So our primary purpose today is just to kind of get us refamiliarized with the ionic and net ionic equations. Because if you look at the lab that you're doing today, tomorrow, and if you look at the PLTL that you're doing Wednesday, Thursday, you're going to see that everything in there is all double replacement reactions, reaction types, balancing equations, and this net ionic equation stuff. So one of the reasons why I kind of pulled back and didn't finish this before break was because I saw this thing coming, and I wanted to make sure that we kind of had a chance to reintroduce this to ourselves before you're asked to completely put it into practice in lab. Because technically, the original topic for today was stoichiometry, calculations in chemical reactions. And I wanted to make sure that we had a chance to kind of actually talk about what you're going to see in lab this week, which is completely different from that. So first things first, what we want to look at with this equation is, first of all, can we identify this equation in terms of type? What kind of a reaction is this? Combination, decomposition, single replacement, double replacement, combustion. Which one is this? This is double replacement. How do I recognize double replacement? What I'm looking for are ionic compounds. If I have two ionic compounds as reactants and two ionic compounds as products, that is double replacement. If I only have one ionic compound on each side, that's single replacement. That's the difference between the single and the double. How many ionic compounds are on each side? Double has two, single has just the one. So I know that this is double replacement. The other thing that I can look at, characteristic sign of double replacement, is ion swapping. I can see that the copper and the lithium here have switched places. That tells us right away that it's a replacement reaction, because that's where we see that kind of switching. And then the two compounds tell us it's double and not single. So that's the first part here. We've identified this. This is double replacement. Is this equation balanced? Answer here, no. How do we know that? Well, quickly, we could do a little bit of atom math here. And see that, yes, copper has one each, but I've got two acetates on this side and only one on this side. I've got two lithium on this side and only one on this side. Sulfur is, in fact, still balanced. One of the nice things about double replacement reactions, and any replacement reaction in fact, is because the ions aren't actually changing, it's easy to track them. I can track them as whole ions instead of splitting them apart into carbon, hydrogen, and oxygen. And so from that, I can look at this and say, okay, that's how I know I have two of them. I can also see very clearly that the lack of balance is in the acetate and in the lithium, and they happen to be in the same compound. So to balance it, I just need a 2 there. So that's the first part. I've identified the reaction. I've balanced the equation. Now the question is, how do I break these apart into ionic and net ionic pieces? And to answer that question, I have to know something about the materials themselves. So in particular, I was told that these two are aqueous. Since these two are aqueous, the copper 2 acetate and the lithium sulfide, I know that they are soluble. Now, what else can I pull on if I didn't have that information? This is where my solubility rules would come in. I could look at that solubility rules and say, okay, wait. Lithium is in group 1. All group 1s are soluble. So I know that the lithium is soluble. And I can look at the acetate and come to the same conclusion. Acetates are always soluble. So the copper 2 acetate must be soluble also. So that covers the reactant side. What about the product side? Well, on the product side, I can see lithium and acetate over here. So I know that it's soluble because lithium is always soluble. Acetate is always soluble. That must be a soluble compound right there. What about the copper 2 sulfide? Well, if I go back to my solubility rules, I can see that sulfides are usually insoluble. However, if they are with any of the group 1s or with these group 2s, they would be able to dissolve. Copper is not a group 1, it's not a group 2, so it's not an exception, it must be the rule. The rule is insoluble. So copper 2 sulfide is in fact insoluble. So now that I've identified all of the solubility rules, all the solubility characteristics, now I can break it apart into ionic and net ionic equations. Remember that for an ionic equation, if it is soluble, I just break it apart into the ions that make it up. And the easiest way to know how to break it up is to say the name of the compound. So our first one is copper 2 acetate. So I'm going to have the copper 2 ion, and I'm going to have the acetate ion. What do I do with this 2? Well, that 2 tells me that I have 2 acetate ions in the compound. So I would need to put a 2 out in front there. For the lithium sulfide, lithium ion and sulfide ion are the 2 ions. The 2 in the lithium tells us that there are 2 lithium ions there. On the product side, the copper 2 sulfide is insoluble. Since it is insoluble, it is not breaking apart because it's not dissolved in the water. We're going to leave it exactly the way that it is. And for the lithium acetate, again, it's lithium acetate, so lithium ion and acetate ion. This time, the 2 out in front means that I'm going to have 2 of those ions, each ion in the compound. So 2 lithiums and 2 acetates, because there were 2 lithium acetates. So this is my ionic equation. I've taken all of the things that are soluble and I've broken them apart into the ions that they are made from. To turn it into a net, I need to look for spectator ions. Does anybody remember what a spectator ion is? It's been 2 weeks. Let's think about it. What is a spectator? What does a spectator do? It watches. Okay? Are there any ions in my equation that are just watching, that aren't actually participating in the reaction? What about the lithium ion? Did the lithium ion actually do anything in this reaction? It was exactly the same as a reactant as it was as a product. Nothing changed for it. That's the definition of a spectator. Nothing changed. It participated in no way in the reaction. So with that in mind, is there another spectator? The acetate. Yep, I've got 2 acetates here. I've got 2 acetates there. Nothing changed among them. To turn my ionic into a net ionic, I'm going to remove those spectators and focus just on the things that changed. So what changed? I had copper ion that reacted with sulfide ion to make copper 2 sulfide. The substances here at the beginning are different from the ones at the end. These ones were dissolved in water. These ones are not. That's the difference. That's how we know something happened, that something reacted. So this is the very last thing that we did on, well, it's been 2 solid weeks. This is where we were 2 weeks ago, though. All right, any questions with this? Don't worry, we've got more examples. All right, let's look at this third example here. We've got sodium hydroxide reacting with sulfuric acid, makes sodium sulfate and water. Now, this is not quite the same as the last kind of thing that we did. First of all, we're dealing with acids and bases, not solutions. So sodium hydroxide is a base. Sulfuric acid is an acid. The funny thing about acids and bases is that they all dissolve in water, or at least all the ones that we are going to be talking about dissolve in water. So we can't use solubility as a factor for figuring out whether or not something breaks apart or doesn't break apart. We have to use strength to do that. But before we can get to that, we're going to have to do some balancing here. And it's the same kind of thing that we saw. So sodium, hydroxide, hydrogen, sulfate, sodium, hydroxide, hydrogen, sulfate. Now you may be saying to yourself, oh, wait a second. I don't see hydrogen or hydroxide in the products. In these kinds of neutralization reactions, we can think about water as being hydrogen hydroxide. So every single water molecule has one hydrogen and one hydroxide. That way we keep things straight and neat when we're trying to determine if the equation is balanced or not. So for sodium, I had one hydroxide, 2 hydrogen, 1 sulfate. On the product side, I had 2 sodium, 1 hydroxide, 1 hydrogen, 1 sulfate. So this was a little bit more messy than the last one. I don't have all of the things that are unbalanced all in the same compound. So what I'm going to have to do is I'm just going to have to start balancing what I know and making adjustments along the way. So, for example, I know that I need to balance out the sodium here. So I need 2 sodium hydroxides to give me the 2 sodiums that I need to balance it out. When I do that, though, not only is the sodium balanced and given a 2, the hydroxide now has a 2 as well, which means that my hydroxide is now out of balance along with my hydrogen. Now I can see that if I put a 2 here, that would give me 2 hydroxides and 2 hydrogens. Now everything is balanced out fully. So I've got my equation. I've got it balanced. Now I need to figure out what's breaking apart and what's staying together. To do that, I need to go into looking at the solubility rules again. Sodium hydroxide is a strong base. As a strong base, it's going to break apart completely. How does it break apart? Well, it's going to break apart into the sodium ion and the hydroxide ion. And I'm going to have 2 of each of those because of this coefficient of 2 on the outside. Sulfuric acid is a strong acid, so it's going to break apart as well. Hydrogen ion and sulfate ion. This 2 means I'm going to need 2 hydrogen ions for balancing. On the product side, I've got sodium sulfate. Sodium is in group 1. All group 1 salts are soluble. So I know that sodium sulfate is going to break apart because it is soluble. So I'm going to need sodium ions and sulfate ions. And the 2 here give me that I have 2 sodium ions as a result. Now, what do I do with the water? Is water an acid? Is water a base? Is water a salt? It's none of those things. What do I do when I have something that's none of those things? I can use a generic term for it. It's a non-electrolyte. Any pure liquid like water is a non-electrolyte. Any gas like carbon dioxide is a non-electrolyte. What do I do with non-electrolytes? Well, since they're not electrolytes, remember electrolytes are ions, they split apart. Since it's not an electrolyte, it stays together. So those two water molecules stay together. There's my ionic equation. Let's turn it into a net. Turn it into a net, I need to identify spectators. Can anyone give me an example of a spectator here? What's one of the ions that's not doing anything? Sodium. Yeah. Sodium's on both sides, didn't participate. Any others? Sulfate. Yeah. Sulfate's over here, and it's over here. It didn't participate either. But the hydrogen and the hydroxide, they aren't present on the product side. So we know that we need to keep them as they are. So turn this into a net. I take out the spectators. It's hydroxide plus hydrogen makes water. So if you write it like this, that's perfectly fine. That's just recopying what was in the ionic equation. You might notice that all of those have a coefficient of 2. And so another way to represent this would be in the reduced form. Hydroxide plus hydrogen makes 1 water. And that would be acceptable as well. I can't speak for mastering. I don't know what exactly they look for in their equations. But if you're pretty sure that you did it correctly, and you have it in this first form, try entering it in the reduced form and see if it accepts it that way. I've worked with a number of different homework platforms. Some of them have been super picky about coefficients. Others haven't been. I don't know for mastering for sure. This is the first course I've taught in mastering that I've had to teach this particular concept. All right, questions with this? Are we starting to make some headway? Getting some traction here? All right, give you a chance to earn a couple of participation points here. If you are logged into Pear Deck, go ahead and just put in a ZZ here. Now I'd like you to try this one yourself. I've already gone ahead and balanced it for you. What I want you to do, I'm going to give you about 6 minutes to do it. Try to identify what is soluble and what is not soluble. Turn it into an ionic equation. Turn that ionic into a net ionic equation. In about 6 minutes, I'll post the answers here, and you can kind of check yourself, see how you did. I'm going to walk around and try to point you in the right direction if you got a little bit stuck. And then we'll wrap things up and call it for today. Okay, just about out of time. Let's wrap up here. Okay, so the key here you had to identify what was soluble and what was not. So that list that I projected there, that's in your lecture materials. That's in the chapter 7 folder. So if you're going through this tomorrow night, have that open somewhere so that you can access it and know exactly what's soluble and exactly what's not soluble. Once you did that, you needed to break it apart. The lead chloride was the thing that was insoluble, that was the thing that you needed to stay together. That's what led you to this net ionic equation here. So as you're getting ready to leave, thank you for staying with me the extra minute here. This will pop up on your screen. I'll also go back to here so that you can answer both and get what you're looking for. Oh, good. I forget that it shuts it off on your side. Okay. Look for an email announcement from me later on today, just to remind you of what's coming up and what you need to work on in between classes. Have a great day.